Hey everyone, we have a snow day today, so I thought I would just make a video and record some of the topics that we would have discussed in class. So what I want you to do is log in to Blackboard, and we're going to get some files to help us start out today's lecture. So in the content section, go to Unit 2, and I want you to grab the Asteroids update and download that. That's a zip file that has an updated version of the Asteroids project that we've been working on. So after you download that, you can of course unzip it and open it up inside of Visual Studio. And if you run it, you can see I've made a couple changes since the last video I posted. Some of the changes: I've added a HUD element, some UI up here. I've made the ship itself smaller. The asteroids move a little bit more slowly, the ship moves a little bit more slowly, and I can't hold down the space bar to shoot. I actually have to tap the space bar now. You can see how I do, how I accomplish a lot of these things, of course, by just looking through my code. I'd encourage you to take a look at how I accomplish getting the bullets to shoot with just a keyboard tap. I've created a couple different things. The properties in my Game 1 class, I've created a keyboard state property, and I've created another keyboard state property that I call keyboard state previous. And what the keyboard state previous does is at the end of every update, it stores the current keyboard state so that during the next update, we have the state of the keyboard what it was on the previous update. This allows us to detect when a key on the keyboard has just been tapped, because the keyboard state, and in the current keyboard state, it will be pressed down, and on the previous keyboard state, it won't be pressed down. So that's how you determine those kinds of things. You can actually see that I've made a convenience function called onPress. So if you scroll down a little bit here, I've created this onPress function. You pass in a key to it, and first of all, it just checks for safety to make sure that keyboard state and keyboard state previous aren't null, and then it checks to see if that particular key is down for the current keyboard state, and it checks to see if that particular key is up for the previous keyboard state. So that gives you an idea how I accomplished that. Now for the HUD elements, I've actually created a HUD class. And the HUD class is very simple. It just contains, in this case, 6 different sprites that I load up, and then I set their position, and then every draw, I just draw each of them. Now, this HUD does not actually respond to any sort of actual in-game health system. So even though it is the ship's health, I am not yet tracking the ship's health. But I did want to have a HUD in there for today's example, so you can kind of see how I accomplished some stuff with that. I think that was everything I wanted to point out. So without further ado, let's jump in and let's make some changes to this code. Today, the biggest thing I want to talk about is I want to talk about cameras. How do we program a camera, in this case in a two-dimensional environment? We're making a 2D game, not a 3D game. It's an entirely different animal in a 3D game, but some of the principles are mostly consistent. A camera is not, we have to stop thinking of it as an actual physical object. We can kind of get away with thinking of sprites as like actual images on the screen, but a camera is really just it's math. It's just numbers. Now, how does a camera work? If we're just thinking of a two-dimensional orthographically projected camera, when the camera moves to the right, what's actually happening is everything on the screen simply moves to the left. And if the camera moves to the left, everything that's being rendered on the screen just moves to the right. And that's all a camera is in a 2D environment like this. So how do we actually create a camera? Well, what we're going to do is we're actually going to create a class. So I want you to right-click on your project, and we're going to say Add Class. And the class name should be Camera. Please remember to capitalize your class names. So it should be capital C, Camera. And here we go right here. The camera class itself does not need to be a subclass of anything, because it's incredibly simple, the camera class. Now we are going to use, we're going to give it some properties, like some vector2 properties. So we do want to bring in, oh dear, we do want to bring in the Microsoft .xna.framework namespace. Now, what does a camera actually need? Well, all a camera is a position. It's just a position, in this case in two-dimensional space, that all of our other sprites have a position relative to the camera, and that's how they know where to draw. So what we're going to do is give this camera a vector2 called position, and by default you could set it equal to a new vector2 0 0. And I don't know if you know this, but there's actually a convenience property here. We can actually say vector2 dot 0, and that will actually give us a vector2 starting with a value of 0 0. And we should probably also allow our camera to update, because our camera has to follow something else around the screen. So we're going to give it a public void update method. Okay, and there are a lot of different ways we could do this, but basically what I'm going to do is I'm going to say in this environment we give the camera a target position. Okay, and in the case of this Asteroids game, what I want the camera to do is follow the player's ship around the screen. Now, inside of the camera class, we do not have access to the player's ship, but we can, when we call camera.update, we can just have the game1 class pass in the ship's position. So what I'm going to do is just pass in a vector2 that I'll call target. So that'll be our target position that we want the camera's position to equal. Now, for now, what I'm going to do is just set the camera's position equal to the target position. Later on, what we can do is we can come back to this and we can add some movement so that the camera actually chases the target instead of being locked onto the target. So now this is all a camera really is, and we're gonna make this a little bit more sophisticated. But in the past, previous games I've made, I haven't really gone much further than this. What I end up doing is if I make the camera globally accessible, and I'm not going to go down that rabbit hole, but if I did, every sprite in its draw method could access the camera and create a temporary position, a draw position, by simply taking its own position and subtracting the camera's position. And that would work quite well. But it's not optimized, it's not ideal for a couple different reasons. But that is essentially the mathematics behind what we're going to do here. The much better, the much more sophisticated way of doing this in any game engine is to use something called a matrix, or multiple matrices. And perhaps you've heard of a transformation matrix before. We're not going to get too deep into the math of it, but the mathematics behind it are pretty interesting. But let's go ahead and create a property in this camera class. The data type is matrix, and that is defined in the Microsoft.xna.framework namespace. And I'll just call the property matrix. And let's see, do I want to instantiate it right now? I think I do, actually. I'm just double checking my notes here. Yeah. So we're going to say matrix equals a new matrix. And what we want to do is basically create a new matrix every single update. Now, you might be asking, what is a matrix? Well, in your homework assignment, that is in the Unit 2 folder, the cameras assignment, there are several links in there, resources. And I hope you guys check these resources out when you do your homework assignments, because I throw them in there because I think they'd be somewhat helpful. They are some very good resources that talk about matrices in varying levels of detail and mathematical detail and information. So some of these links have to do specifically with XNA. But if you want to look at this graphic right here on the screen, this kind of represents what a matrix is. If you remember what a vector is a vector is just a collection of numbers. Now, right now we're working with two-dimensional vectors, so these vectors store two numbers. There are also three-dimensional vectors, and you can have vectors with more dimensions if you want. And a matrix is kind of like a vector in the fact that it's got lots of numbers. It's just a collection of numbers. And what these numbers do is they actually allow us to do a mathematical formula on our vectors, and that formula, that mathematical function, is called a matrix transformation. Normally, this article does a pretty good job of saying or describing the need for matrices. If you consider this triangle right here, this is a triangle that we're familiar with from the classic game Asteroids, which we happen to be creating a clone of. If we render it on the screen, and we can think of it as 3 different points that are all relative to a center point here, and what the ship has to do in the game of Asteroids is occasionally rotate or translate around the screen as well. Now, in the game of Asteroids, it doesn't really ever need to scale that I'm aware of, but scaling is another kind of transformation. So in order to find these new points, if you were to rotate this ship around its center point, you'd have to do some trigonometry. Okay, and it's not too terribly difficult to figure out the math behind it. But what ends up happening is, if you try to calculate the transformed point for all 3 points here, you actually have to calculate sine and cosine multiple times. Now, sine and cosine are very expensive on the CPU to calculate. So it works for a single triangle, but the article actually shows us a much more sophisticated shape right here. And for the processor, for the CPU, to do sine and cosine for every single one of these points would be overkill. It would actually bring the processor, it would slow it down. In fact, if you had hundreds or thousands of sprites on the screen and you had to constantly be using sine and cosine to figure out how to rotate the object, it would slow your game down quite a bit. So the solution here is to use a transformation matrix. What you basically do is you calculate things like how much you want to rotate the object, how much you want to scale the object, and it figures out a series of numbers that make up a matrix. And you can actually combine multiple matrix transformations into a single collection of numbers, into a single matrix. So you can do a rotation matrix and then multiply it by a transformation matrix and then multiply it by a scale matrix, and then if you take that matrix and you apply that transformation to a single vector or multiple vectors, you can do all of those transformations one after the other. So they're pretty sophisticated, and these articles are worth checking out. So the code behind it. Let's get to the code. What I want to do is every update, I'm just going to reset the matrix back to having no transformation. And what we do is we set it equal to a matrix called the identity matrix. And the matrix class has a static convenience property here that actually stores the identity matrix. So we just say matrix equals matrix.identity. Now what I want to do is multiply my current matrix by another matrix. And that matrix will be a transformation matrix. So what I'm going to do is multiply my current matrix by matrix.create, and what I want to do is create a translation matrix. So there are 4 different overloads for the create translation method here. I'll use overload number 3. What we're going to do is provide it with an X translation, a Y translation, and a Z translation. Okay, and as you might be able to guess, how far we want to translate, we already have stored inside of our position here. So let's try this. Let's say position.x, position.y, and 0 for our Z translation. These matrices inside of X and A are built to work for 3D and 2D, but we're just going to ignore the Z axes here as we work. So now that we have a matrix, how do we actually use the matrix to move everything on the screen when it's drawn? Well, this ability is already built into the sprite batch. And it's really fantastic. If we go into the Game 1 class and we go down to the draw method, when we call spriteBatch.begin, there are some overloads for this method. What I'm going to do is erase the opening parenthesis and rewrite it. And you'll notice that there are 5 overloads. Overload number 5 is the one we want, because if you look at the very last argument there, it is a matrix, a transformation matrix. So what I'm going to do, actually we don't have a camera created yet. I want you to scroll up to the top of your Game 1 class and let's create a camera. So I'm going to say camera cam, and then I will scroll down, and either in the load content or the initialize, let's create that camera. So I'll say cam equals a new camera. And we didn't give the camera a constructor that takes any parameters, so we don't have to worry about passing anything in. Okay, now what we can do is we have to make sure we update the camera every single update. And we're going to, after we say ship.update, we're going to say cam.update, and we have to pass in a target. Now I want the camera to follow our hero's ship around the screen, so we're just going to pass in ship.position as our target position for the camera. Okay, so our camera's position is always going to equal the ship's position. And every single time we update the camera, it calculates a new transformation matrix. Now, down in the draw, when we say spritebatch.begin, we're going to overload this with overload method number 5. Okay, now there are several different properties here. The first one we have to pass in is the sprite sort mode. This actually tells the sprite batch how it should sort the individual texture 2Ds before it draws them. And when I say sort, I mean the depth. And as I told you in class, I think the first week, right now they are being drawn in the order that spritebatch.draw is being called. And basically, I just want to leave it that way. What I'm going to do is pass in sprite sort mode dot deferred. Deferred is the one that makes it so that the order you draw them in is the order that they're drawn in. The next thing I have to pass in is a blend state, and I believe for most of these properties I can just pass in null, and it will allow these properties to default to their default values, and we don't have to overthink it. I'll try passing in null for effect, and then we have to pass in a transformation matrix. Luckily we can get that by saying cam.matrix. Now I believe I did not make my matrix property public, so let me just jump over to camera real quick. I'm going to make matrix public. Apparently I cannot type. There we go. Jump back to game 1, and doesn't look like we have any errors here. What I'm going to do is run my game, and notice it looks weird. And we do have some camera movement. It's kind of interesting. The ship moves, but the camera kind of moves in the opposite direction of the ship, and as you'll notice, the camera is not locked onto the ship. Well, the fact that the camera is moving in the opposite direction as the ship, or actually, I'm sorry, it's moving in the current direction as the ship. No, sorry, everything is moving with the ship, and it should be moving the opposite direction of the ship. What I want to do actually is go into my camera, and when I calculate my transformation matrix, I actually have to move everything the opposite direction that the camera moves. Okay, remember when I said that? So what that means is making sure that when we create our translation, we pass in a negative position.x and a negative position.y. So now when I hit F5, you'll notice that everything now seems to work, except the player ship is in the upper left-hand corner. Okay, now this is good. This is a step in the right direction, because if you notice, as the player ship moves, the camera is locked onto the player ship, but the player ship is not in the center of the screen. What we've just done is we've done something called a world transformation. Okay, now let's think about it real quick. If we have the player ship and the player's X position is 500, okay, and we're telling the sprite batch to use a transformation matrix that moves everything in the opposite direction as the player's position. What we're essentially doing is we're taking the player ship and we're saying in the world you're at X position 500. And then when we draw you to the screen, we're going to subtract 500, which is going to put your X position back to 0. Okay, the same thing is happening for Y, the Y position, and it's going to happen no matter what that value is. So how do we fix it? Well, we have to do another transformation. So this first transformation, and I know I'm really bad about putting notes, comments in my code, but this first transformation is something we can call a world transformation. Okay, we're translating the entire world to follow the camera. Now what we have to do is we have to then do a screen transformation. So we have to take the entire world now and move it out of that upper left-hand corner. So if I want the player to not be in the upper left-hand corner at 0, 0, what we basically want to do is grab the entire axes and move them to the center of the screen. Well, what we can do is say matrix times equal. We're going to take the matrix and we're going to multiply it by another matrix that we're going to get by saying matrix.createTranslation. And we're going to do the third overload again. And basically, we just want to take everything and we want to slide it from that upper left-hand corner into the center of the screen. So if your screen is 800 pixels wide, you want to slide everything to the right 400 pixels. And if it's 480 pixels tall, you want to slide everything down 240 pixels. And then we're not going to worry about Z. Okay, so this first one slides everything up and to the left, and then the second one slides everything down and to the right. Actually, I'm sorry, this first one slides everything up and to the left only if the ship is down and to the right relative to the world origin. Some of this would be much easier to explain if I had a whiteboard and I could just draw on it. But let's go ahead and hit F5 and see what happens. Yes, now the player ship is in the center of the screen, and you can use the arrow keys and the ship will move, and it looks like it works well. In fact, you could say it looks like it works a little too well. Notice that the background moves, which looks good until you can kind of see the edge of the background. Notice also that the HUD moves, and the game does feel a little odd now that we have clamping, so the player can move to the right or down a certain distance, but then is stopped by that clamping we added 2 weeks ago. Also notice that if we go up high enough, we can see the area where the asteroids are spawning. So we can just kind of see them popping into place. And if we go down far enough, we can see the area where they're being disposed, where they're disappearing. Okay, so we have a lot of stuff that we need to fix here before we could call this, a more polished game. So let's see. Let me check my notes and see where we what we want to fix next. I think. Actually, before I jump into anything into anything new, I wanted to point out a couple more things about transformation matrices and why they are so powerful. I think I said earlier that a transformation matrix would also allow us to scale the entire world, or would allow us to rotate the entire world. And I can show you a quick example of that. Right here, where we're calculating our transformation matrix, we can scale everything up or rotate everything by taking our matrix and multiplying it by another transformation matrix. Now, instead of doing a translation, let's do a rotation. So let me just rotate the entire world 180 degrees. 180 degrees would be pi in radians. So if I do that, I have an error, and what is my error? Okay, I need to pass in a float, and math.pi is a double. So let me just throw a float in front of there. Hit F5. And notice that this might not be what you expected. Now, we did flip the entire world 180 degrees. But the order that you do these matrix transformations is very important. So all of your matrix transformations happen about the world the screen origin in the upper left hand corner. So if you do a rotation, it's going to rotate everything around the upper left hand corner of the screen. To get a better idea of what I mean, what I'm going to do is I'm going to create a value in here that I just call spin, and I'm going to set it equal to 0. And then every single update, what I'll do is I'll just add to spin. I'll say spin plus equal 0.01f. And then instead of rotating 180 degrees, I'm going to rotate or spin radians. So if I hit F5, the world should now be spinning. And notice that it's spinning about the upper left-hand corner of the window. Okay, that it is always going to happen. It's always going to spin about around the upper left-hand corner. So how do we get it to say spin around the ship? Well, that's actually really simple if you think about it. The ship is in the upper left-hand corner before we do this second translation. So if we just change the order that we do these matrix transformations, we can really drastically change the results on the screen. So the first thing that's happening is we move the ship to the upper left-hand corner, then we rotate the entire world, then we move the ship out of the upper left-hand corner into the center of the screen. So now if I hit F5, you'll notice that the ship stays in the center of the screen and the camera rotates, which, is very disorienting. Probably not something you want to do. You can do the same thing with scale, for example. I'm going to create a float called scale, and what I'm going to do is set it equal to 1 times 0.5f, no, 1 plus 0.5f times math.sine of the spin value. I can't type a single line of code without making typos. Okay, math.sine returns a double, and scale is a float, so I'm going to cast math.sine as a float, and then we should be good there. And then instead of doing a rotation here, if you want to keep that, you can just comment it out. I'm going to do a scale. So I'm going to multiply the matrix by matrix.create scale, and I'm going to pass in that scale property I just created. Now, because I'm doing a sine wave here, the camera is going to zoom in a little bit, then it's going to zoom out a little bit, then it's going to zoom in a little bit, so on and so forth. So the camera zooms in, and then the camera zooms out. And I've essentially kind of attached the camera zoom to a sine wave, so it's just going to bob back and forth like this. And this is only for demonstration to show you that these transformation matrices allow us to do the rotations and the scalings. So I think matrices are just totally sweet, and if you continue your career in game development, you will almost certainly use them if you continue as a programmer. So another couple things to point out about transformation matrices is that these matrices actually, when they end up doing their transformation on all of the individual vectors, on all of the sprites, when it comes time to draw them to the screen, all of the calculation is being done by the GPU. It's being done by the video card. Okay, because the transformation matrices end up getting passed off to the shaders, and the shaders are all running on the GPU and not on the CPU. Now this allows for incredible hardware acceleration, and this is why we have modern gaming. We wouldn't be able to have modern gaming if we didn't have transformation matrices and if we didn't have shaders that were calculated on the GPU. Also, the results of using transformation matrices instead of just doing vector math are much better. You don't get any tiny little gaps. I've actually, like I said in the past, I've created cameras without transformation matrices, and sometimes what you'll get is you'll get little rounding errors, and you'll get tiny little gaps between your sprites. So if you're trying to create, say, like a tiled background, if you don't use a transformation matrix, it'll get messed up. So anyway, enough about me just talking about transformation matrices. Let's keep on with our project here, and let's fix our HUD. So the problem with our HUD is that it's being drawn in this sprite batch, and everything that's being drawn in this sprite batch is being moved by this matrix. So the secret to having this HUD not being affected by this matrix would be to put it in its own separate sprite batch call. Okay, so what I'm going to do exactly that. I'm going to take HUD and I'm going to move it out here, the HUD.draw anyway, and right now I'm in game1.draw, and I'll wrap it in its own sprite batch.begin and sprite batch.end. Okay. Notice that this sprite batch.begin is not using a transformation matrix. Okay, so the HUD will not be transformed. See, now the world moves, but the HUD does not. Now, if you are creating a two-dimensional game and you want to create a sense of parallax, okay, or you want to create elements that don't move with the camera, say like HUD elements and other graphic elements, you just have to put them in their own sprite batches. So let's say I didn't want the background to move with the camera. What I can do is, I still want to draw it before I draw everything else. So up here, I would create a new sprite batch.begin and sprite batch.end. And then I would move my background draw call to be up here. So now when I hit F5, the background doesn't move and the HUD doesn't move, but the ship does and the asteroids do. And that's a good start. Okay, we should do some things. We should remove the clamping on the player's ship so that they don't hit the top of the bounds or the sides. And we just go into the ship class. We go to update, and this is where we're doing the clamping right here. And we're just going to comment that out. So wrap that in some comments. And now, of course, our player ship is no longer being clamped. It can fly outside of the original playing area. Sometimes it's hard to tell if the player ship is moving since the background doesn't move now and there are no indicators, other indicators. But I'm not going to take the time to fix that. You can fix that with like particle effects coming out the back of the ship, or by having a little bit of parallax on the background, but I'm not going to worry about it. Now, we've got a couple problems. Notice that when I shoot the bullets, they're being told to despawn when they hit what was formerly the sides of the screen. And so if I'm actually outside of the original play area and I hit the spacebar, I don't shoot any bullets. And this is a problem, obviously. So what we need to do is come up with a new way of determining when the bullets and asteroids should be removed from the game. And there's a couple different ways we could do this, but essentially what we're trying to do is we're trying to figure out when are the bullets no longer in view of the camera. When are the bullets no longer in view of the camera? Because if they're outside of the camera, then we can probably safely say that we're done with them, and then we can remove them. Then we can mark them as dead. So we don't want to do it like this anymore. So I'm in the bullet class. I'm just going to comment out what we had before, where we were setting the bullets to be dead when they hit the sides of the screen. What we want to do instead is figure out when they're in view of the camera. And I'm going to create a separate method for that, in fact. And the method, I'm going to call it, it's public void, I'm going to call it cull, C-U-L-L. Cull is a term in video game design that basically means if an object is outside of the view of a camera, then you cull it. And culling typically means to just not render it. But in this case, with the bullets, I'm going to set them as dead if they are outside of the view of the camera. So how do we know if it's outside of the view of the camera? Well, I'm going to solve this very simplistically. And to do it, I'm just going to get the distance between this bullet and the camera. And if the distance is big enough, then I'm going to cull it, or I'm actually going to dispose of it by marking it as dead. Okay. Now, the bullet does not know the camera's position. So what I can actually do is when I call bullet.cull, I can pass in a camera object, and then I can get that camera's position and use that position to call the bullet. So if you remember what we did in last week's video, we were able to get the distance between two objects by using the Pythagorean theorem. So to do that, I usually calculate the distance x between two objects. In this case, it's camera dot, oh, the camera's position is not public. So real quick, we're going to go to the camera class, make its position public. Okay, there we go. Back to the bullet class, we can say camera dot position dot x minus this object's position dot x, and that's the distance x between the two objects. Now I'll just do a copy and paste here and change these to y, and now we've got the distance y between the camera and this object. Now, if you remember, the Pythagorean theorem would allow us to say the distance between the two objects is equal to math.square root of dx squared plus dy squared. Okay, math.square root returns a double, so I'm just going to cast this as a float, and then we should be good to go. Now, what I'm going to do is say if the distance between these two objects is greater than some distance, then this object must be dead. So if the distance between the camera and the bullet is greater than, I don't know, I'll just pick 200 for now, and we'll come back and change that. If the distance is greater than 200, then the bullet is dead. Okay, let's test this out. First of all, we have to call the call method. And what I'm going to do is actually call it right after I call the bullet's update method. So go into the game1 class, and let's find bullet.update. Okay, here's the for loop inside of game1.update that loops through all of the bullets. Notice I've got bullets number I.update. Right after that, I'm going to say bullets number I.cull. Oh, and I have to pass in a camera object, so I'll pass in the cam. Okay, so now if we run the game, if a bullet is ever 200 pixels away from the camera's position, that bullet will mark itself as dead, and if it marks itself as dead, it should be removed. So let's hit F5, and sure enough, if I shoot the bullets, you'll notice that they travel a certain distance away, and then they just disappear. Now, 200 is just kind of an arbitrary number I picked, of course. What we need to do is probably store a less arbitrary number to use instead of 200 for our cull distance. What I'm going to do is go into the camera class, and I'll create a public property in here that I will actually call cull dis, and I'll set it equal to 550. Now, 550 in this case is not an arbitrary number. It's a number that I tested earlier, and I found it to work quite well. It would probably require a little bit of trial and error on your part if your resolution is different than mine. Mine is 800 by 480. Also, it might require a different number depending on the sizes of the sprites that you want to cull. But we're not going to get too sophisticated here. We're just going to say cull distance equals 550. So now what I can do is jump back to my bullet.cull method, and I can say if the distance between the bullet and this object, or excuse me, the bullet and the camera, is less than that camera's cull distance, then the bullet is dead. So if we hit F5, we should no longer see the bullets disappearing, and we can head as far away off screen, quote-unquote off screen, as we want, and we can still see bullets. Now, this makes me a little bit uncomfortable because there's no visual proof that the bullets are actually being culled. So if you're like me and you want to double check, I'll just go into the game1 class. After looping through all of the bullets, every update, let's just say console.writeLine, and let's write out the number of bullets that we have. So it would be bullets.count. Okay, hit F5, and while your program is running, you should have an output window. In fact, it's probably will be down here. You'll have to probably click on it. I have mine pinned open. And right now, every update is printing out 0, which is appropriate because there are 0 bullets. If I start shooting bullets, that number should go up. Oh, let me scroll down here. It's scrolling up. Oh no. Okay, if you ever scroll up in this output window, it refuses to scroll down. I guess what I can do is quit my program and then restart it. There we go. Now I will shoot bullets, and I can see that number go up, and then I can see that number go back down. That's a pretty safe assurance that those objects are being disposed. Now I'm just going to comment out the console.writeLine. If you've got a lot of console.writelines in here, it'll actually slow your program down, so just use those for debugging purposes and not actually at runtime. Okay, so we are properly culling our bullets, and that is a great start. However, if we want to optimize our code, there is a way to optimize the Pythagorean theorem to run even faster. Okay, and if I jump back to the bullet class, the math.square-root method here is very expensive. Okay, it's like the cosine and sine methods are expensive. The square root method is expensive on the processor. And when I say expensive, I mean it just takes longer to calculate than most other mathematical formulas that the processor has to calculate. So there is a way we can actually do the Pythagorean theorem without getting the square root. And if you think back to just basic algebra, if we want to remove the square root from this side, all we have to do is square the other side. Okay, so what I'm going to do is comment out this line, and instead of getting the distance, I'm going to get the distance squared between the two objects, and that value is just dx squared plus dy squared. So it's like the Pythagorean theorem, but without the square root. Now, if I square this side of the equation, I have to square this side of the equation. So I can say cam.coldistance, or cam.coldistance times cam.coldistance. Now this is going to be much more efficient on the processor. So if you have to call, hundreds of objects every update or thousands of objects every update, this is going to be the way you want to go. Now, this could still be better. There's no reason why we should, for hundreds or thousands of objects, have to recalculate the call distance squared every single update. That's a value that could be stored inside of the camera as well. So you could come in here, you could create another float called call dis squared, and you could set it to a constant value, or you could, for example, in the camera's constructor, just say call dis squared equals call dis times call dis. Now these are both public, which means that they can be changed, and unfortunately the call distance can be changed without changing the call dis squared. This is something I wanted to go over with you guys in class today, some neat tricks we can do, but I'm not going to do it on the video today because it would just make the video that much longer. So now, if we calculate call dis squared once when the camera is created, back in our bullet.call, we can compare the distance squared to cam.calldis squared. And we're doing even less math, which the processor just loves. It loves doing less math. Now, the other thing you could do is, instead of doing a circular absolute distance between the two objects, you could do an axis-aligned bounding box. So kind of similar to this, but instead of these constant values of -10 and 490 and 810, you could calculate the 4 edges of the screen every single update based off the camera position. And that wouldn't be too hard to do, but I'm just going to do it this way for today. Now we can create this same call method inside of the Asteroid class, and I'm going to do exactly that. I'm going to just copy the whole thing, go into the Asteroid class, and I will paste it in here, and I will comment out where we're marking the object as dead inside of the update method. Okay. Now, there's one more way you could optimize your code here for readability. Not necessarily at runtime, it wouldn't run any faster. But I want you to know that finding the distance between two positions, that math is already done for you as well. So what we could do is, instead of doing the math ourselves, we could say, the difference between the camera's position and this position we can find by just subtracting the one position from the other. That'll give us a new vector, and then we can get that vector's length by saying diff.length. That's the same as finding the distance between these two positions. Or we can get that vector's length squared by calling the length squared method. So now, instead of this d2, we could just say if the diff dot length squared is greater than or equal to the cam.calldis squared, and then the object is dead. So this is a little easier to write. There's just fewer lines of code, but it's doing the exact same thing as our bullets call method. So it's important to understand the mathematics behind what you're doing. So if you understand this, you can totally use it. If you understand this better, you should totally use this one. So it's up to you. What I can now do is go into the game 1 class, and when I update the bullets, I can do the same thing. After updating them, I can call them. I can say asteroids number I dot call, and I can pass in the camera object. Okay, and this should work pretty well. Of course, notice that if I go down significantly, the place where the asteroids are being spawned is now outside of the call distance, and so no more asteroids will be created. What we now have to do is dynamically change where the asteroids are being created relative to the camera's position. And this sounds pretty tricky, but it's actually not too hard. Instead of having the asteroids fall down the screen, what I'm going to do is use that call distance and then pick an angle at random. And then using that distance as the magnitude of a vector and the random angle, I will spawn the asteroids in random places around the hero's ship, or actually around the camera. So I'm going to go into my game.update where I am spawning new asteroids. It's right here, where I have asteroid 8 equals new asteroid. And what I want to do is pick a position for this asteroid to spawn at. And like I said, I'm going to spawn them all a certain distance away from the camera. And that distance is going to be equal to the camera's call distance. Okay. And then I'm going to pick a random angle, and I'll just store that in a variable called r for radians. And I'm going to just create a new random number generator, and then get a double out of it by calling next, or .next double. Okay, that's going to give me a number between 0 and 1, which if I want a number between 0 and 360 degrees in radians, that would be between negative pi and pi, or 0 and positive 2 pi. What I could do is just multiply this by math.pi times 2. Okay. Now this whole thing is a double. I just want to cast the entire thing as a float. So I'll put the whole thing in parentheses and say float in parentheses in front of it. You don't need that space. And then just make a note here that since you're multiplying the range of 0 to 1 by 2 pi, your actual range here is 0 to 2 pi. Okay, so this r number is going to be a number between 0 and 2 pi, which actually it might be even easier if you write it's a number between 0 and 6.2, 3.148, so on and so forth. Okay, so what I'm going to do now is use this distance as a magnitude and this radian as an angle, and I can calculate a starting position for my asteroid. I can calculate an x and a y. So x is going to equal the distance times the cosine of the angle. Okay, this is going to give me a double, so of course I got to cast it as a float. And then I'll just copy this, paste it, and I'll change it to a sine, and that will give me the value for y. Okay. Now, what I'm going to do is use that x and y to create a new vector 2. So I'm going to create a vector 2 that I'll just call POS for position, and we're going to say equals a new vector 2 at x, comma y. And what we'll do is we will pass that position in as the starting position for this new asteroid. So all the asteroids will start at random locations in a circle around the camera. So what we can do now is we actually have to go into the asteroid class, because remember that this position, as we originally wrote the asteroid class, gets rewritten. So the position here is passed on to the superclass constructor, and then when that constructor is done, this asteroid constructor gets called and the position is overwritten. So I do not want that to happen, so I'll just comment out those two lines. And then we can kind of test it out by hitting F5. and it might be kind of hard to see if anything's happening at all. So what I'm going to do is actually, I'm going to set my default speed to 0, 0, and then I'm going to set my the speed X and speed Y. I'll just comment out those two lines. So now our asteroids, when they spawn, shouldn't move at all. Now it doesn't seem to me like it is spawning in a circle around the player's ship. If you want to double check this, you can do a couple things like go into the game class and change this distance to a smaller distance and see where the circle forms. So let's say 200, and oops, I just hit Control A instead of Control S. Hit Control S, F5, and where are the asteroids spawning? You'll notice that they're actually spawning in a circle around the origin, the world origin, not around the player or the camera. And that's because we've just given them a big circle, and what we need to do is actually add to that vector the camera's position or the ship's position. Okay, so I'm going to add the camera's position, and now you'll notice that they always form 200 pixels from wherever the camera's positioned. Yeah, they're forming a circle, except for this one out here. Actually, notice at the very beginning of the game, the camera's position is 0, 0. So this particular asteroid up there in the upper left-hand corner is actually spawning probably 200 pixels from the original position of the camera, which was 0, 0. Okay, so this is what we want to have happen. And actually, as the player's ship moves, they should continue to always spawn 200 pixels away from the camera's position. And it appears like they do. Now, instead of using 200, we can go ahead and change that to the camera's cull distance. So we're just kind of expanding that up to 550. And 550 should always put these asteroids just outside of the screen. We could test this by moving our ship in any direction, and we should see some asteroids. I'm not even entirely sure that worked. What I want to do actually is I'm going to change my counter spawn instead of being reset every 20, I'm going to set it to 1 so that we just spawn a lot more asteroids. Yeah, okay, so it is working. Perfect. And now I'll set this back to 20. Remember, if you remember, this controls how quickly or how often we spawn new asteroids. Okay, so the only thing now is for us to set the speed of the asteroid so that it moves towards the player's ship after it spawns. Now we could give these asteroids completely random speeds, but more often than not it would probably move, or about 50% of the time, it would probably move away from the player and immediately despawn. You might think this is appropriate behavior for your game, but I think it's kind of a waste, and it seems kind of silly. So what I want to do is use this angle that we've calculated and use it to calculate the speed of the asteroid. So what I want to do actually is I'm just going to change the asteroid's constructor to take 3 arguments, and for the third argument I'm going to pass in that angle. So I pass in R, and of course it's saying, you got a compiler error. So go to the asteroid class, change the constructor to take a float that we can call angle, and now we can use this angle to calculate the speed. So what I want to do is set the speed y to being a speed constant, so how fast you want the asteroids to go, times the sine of the angle. So let's just say we want the asteroids to move at 5 pixels per second. That's the magnitude of the vector we want. And then we'll multiply it by math.sine of the angle. And we're going to do the same thing for x. We're going to say x is going to equal 5 times the cosine of the angle. And notice I've got a compiler error. That's because sine and cosine here are doubles, so I'll just cast them as floats. And then we should be good to go. If you run this, you'll notice that it probably does not work. And that's actually because we're telling the asteroids to move exactly in the opposite direction of the hero. We're telling them to continue along that same angle upon which they were spawned. So what we actually want to do is turn that angle around 180 degrees so that the ships are now moving, or that the asteroids are moving towards the player's ship. Now, we could subtract pi from this, or we can just take our speed vector and set its x and y to negative, whatever the sine and cosine actually produce. So if you take a vector and you multiply it by -1, all you actually accomplish is turning the vector so that it faces in the exact opposite direction. So that's exactly what I'm going to do here. I'm just going to throw a negative in front of that, and then when I play the game, when the asteroids spawn, they move directly towards the camera, which the camera just happens to be fixed directly on top of the player's ship. So the asteroids are always moving towards the player's ship. Now, this the player would probably feel like the game was out to get them. Since the asteroids are always moving directly towards the player's ship, it doesn't feel very natural. It feels very, very targeted. What we can do, actually, is take that angle, and we can add a little bit of randomness to the angle, just a little bit. So we could say add plus or minus 10 degrees, and then or plus or minus 20 degrees, and then the asteroids will still always go through the screen, but not necessarily always go right towards the hero ship. So what I'm going to do is do exactly what I just said, and let me just pull up my example here. I'm going to add to the angle a random number. So I'm going to say angle plus equal, and I'm going to say random.nextDouble, which is going to give me a number between 0 and 1. And then 0, if you remember, 1 in radians is 57 degrees. So what I'm actually going to do is subtract 0.5 radians. And so this is actually going to give me a number between negative half a radian and positive half a radian, or about negative 28 degrees to positive 28 degrees. And I think this will work just fine. And you can play around with this number to get it to look the way you want. And I think this feels much more like asteroids. Now, the only other problem here is that the asteroids are probably moving a little too quickly, and they're all moving the same speed. So of course we can fix that by more random numbers. So instead of typing in a constant number here of -5, what I'm actually going to do is calculate a speed constant. So I'll say float s equals, and I'm going to say random.nextDouble, so I have to cast that as a float. And I'm going to make this a number between 0.5 and 2.5. So that is a range of 2 with a minimum possible number of 0.5. And I'm going to take this s and I'm going to put it here where I have the 5. And then I'll try the game again. And now we should have slower asteroids that are moving at different speeds. And this feels, for the player, to be a much more manageable experience. Wow. So because we're moving the asteroids more slowly, there is a potential for more of them to be on screen at any given time. There's a couple different things we could do, though, to fix that. We could come down here to our spawn counter, and we could increase that so that asteroids are only spawned every 40 updates instead of every 20. Or we could just set a maximum number of asteroids at any given time. So we could say if counter spawn is less than or equal to 0, and if asteroids.count is less than, 12. That's an arbitrary number, but this would make it so that we could never have more than 12 asteroids in our game, or at least not through this code right here. So if we hit F5, if we ever have 12 asteroids, it'll just stop spawning asteroids. And of course, you could go a lot of different directions with this. So we have implemented a camera system. We have changed our bullets and our asteroids to basically cull and dispose themselves when they are far enough away from the camera. We've changed the asteroids' behavior so that they spawn outside of the camera or just at the call distance of the camera, and then they move towards the screen, and then once they go outside of the screen, they are culled. There are a couple other things I wanted to show you, but I'll try to keep it quick here. Actually, I think there's just one more thing I want to show you, and that's would be inverse matrices. If you have mouse input in your game, you're going to need an inverse matrix. Okay, let me show you what I mean. I'm going to let's see, I've got a UFO in here. What I'm going to do is come up here, and I'm going to create a new sprite called UFO, and that's in my Game 1 class. I'm going to go down to my load content, and I'm going to load up that sprite. I'm going to say UFO equals a new sprite, and I'm going to pass in content.load a texture 2D, and that texture 2D, of course, is the UFO texture. Oops, goodness. And I don't know, I'll just set its position to start at 0, 0, so vector2.0. And I want to draw that UFO every single update. So I'm going to come down here to my sprite batch.draw. Now, if you're using your mouse input to affect objects that are in the world space and not in the screen space, that is what I'm trying to address here. So I'm going to draw the UFO in the world space. So it's not a UI element, not a HUD that sits on top of the game, but actually is an object inside the game. So I'm going to say UFO.draw, and I'm going to pass in the sprite batch object. Now if I hit F5, my UFO is being drawn at 0, 0, and if I move my ship, the 0, 0 position itself actually moves, so it looks like that UFO is moving. And there's no mouse input here, but what I'm going to actually do is make it so that the ship, the UFO rather, follows the mouse around the screen. So I'm going to have it be more like a mouse cursor that exists inside of world space. So to get mouse input, it's very similar to how we get keyboard input. I'm going to create a mouse state object by calling mouse.getState. Okay. Now what I can do is I'm going to get the position of the mouse. The mouse state object has an X property and a Y property, and I believe these are integers, so it doesn't have a vector 2, but we can create a vector 2. So I'm going to create a vector 2, and I'll just call it M. I know it's not a very descriptive name, so I apologize for that. And I'll say equals a new vector 2, and the X value of that vector 2 is going to be m.x, or excuse me, ms.x. and the Y value will be ms.y. So I'm getting the X position of the mouse and the Y position of the mouse, and I am using it to create a new vector 2. I will then set the UFO's position equal to that vector 2. So basically the UFO's position should now equal wherever my mouse is. If I hit F5, it seems to work. Oh, actually you can't see the mouse. I'm going to turn the mouse on so that we can see the mouse cursor. Go up to, I'll just do it in the initialize. In the initialize method, I'm going to say, there's basically a property inside the game class called isMouseVisible, and I'm going to set that to true. Now when I hit F5, I can see the mouse cursor, and I can see the UFO is following the mouse cursor, and it seems to work fine. Notice, however, that once the camera moves, the UFO is still following the mouse cursor, but it's displaced. It has an offset here, and that offset, of course, is the distance that the camera has moved. Remember that we're dealing with two different coordinate systems here now. When we implement a camera system, we're dealing with world space and we're dealing with screen space. When we get the mouse's position, it's the mouse's position inside the window. Okay, so if I move my mouse up to, and I'm going to move my camera this way. If I move my mouse up to the upper left-hand corner, it's now safe to say my mouse is at about 0, 0 inside the window. Okay, which is putting my UFO at 0, 0 in the world coordinate system. Okay, so what we're actually doing is when we have the camera and we're passing that transformation matrix into the sprite batch .begin, that matrix is all the math we need to that we need to convert objects from world space into screen space. And now what we need to be able to do to support mouse input in a game with a camera is we need to be able to convert the mouse from screen space into world space. And in order to do this, we basically take our transformation matrix and we have to invert it so that the math is exactly the opposite. So I'm going to go into my camera class and I'm going to create a transformation matrix to be the inverse matrix. And I'll just call it I matrix because I can't think of a more clever name at this point. So we've got matrix, we've got I matrix, and we can calculate the inverse matrix based off of what our matrix is. So once we're done calculating the matrix, every update, we can now say our I matrix, our inverse matrix equals, and we're going to invert our matrix by calling the matrix.invert method. And we're going to pass in the matrix that we want to invert, which is just matrix. This is going to return an inverted matrix, and that's what we store in I matrix. Okay, so how do we use this? Let's go back to our Game 1 class, and we're going to scroll down a little bit to where we were getting the mouse input, right here. And what we basically have to do is take this vector now and pass it through a matrix, which isn't something we've done yet. It's actually very simple. What I'm going to do is we've got the vector, and we are now going to say m equals vector2 dot transform. Okay. Now this is a static method, so we're not calling it on m, we're calling it on the vector2 class. So vector2 dot transform, and then we pass in the vector that we want to run through a matrix. In this case, it would be vector m, and then we pass the matrix that we want to run that vector through, which in this case would be cam dot I matrix. Okay, so that's going to return a new vector that represents this vector running through this matrix, or this vector being transformed by this matrix, and we're going to store that returned vector back into variable m, and then we'll set the UFO's position equal to that. If I hit F5, okay, the UFO is still following my mouse, and if I move my ship, the UFO is still being attached to my mouse's position. So this is fantastic. Now, when would you ever use this? Well, you would use this if for example, if clicking in the game turned your ship towards the mouse, or shot bullets towards the mouse, or if, for example, if in the game I could click on the individual asteroids. Okay, these asteroids' position is in world space, but the mouse's position always starts off being in screen space. So you would always have to make sure that you convert the mouse's position from screen space into world space. Well, I just realized there's one more thing I wanted to show you guys today, and I mentioned it earlier. I wanted to show you how we can get the camera to follow the ship instead of always being locked onto the ship. What I'm going to do is go into the camera class, and I'm going to look at the update method here. And you'll notice that before we do any of the matrix math, we're setting the camera's position to equal the target's position. Now, if we want the camera to follow the target, we don't necessarily want the position to equal the target. So what we want to do is probably give the camera some sort of speed and have the camera move towards the target. Now, this could be as sophisticated or as simple as you like. Fortunately, I've got a method that is very simple, and it's called the exponential slide. It is one of the easiest ways to fake some smooth movement in any sort of programming environment. The results are not always the absolute greatest, but it works very well for most situations. So what I want to do is, instead of setting the position equal to the target, I want to find the distance between the position and the target, and then possibly move the current position half the distance towards the target. I want to move the camera half the distance towards the target. So to do that, I'm going to get the distance between the target and the position, and I'm going to divide it by 2, or in this case multiply it by 0.5, and then remember I want to add that distance to the current position, and voila, this is the exponential slide. Now the only problem is you're not going to notice it. Well, maybe you noticed it a little bit there at the beginning. The reason you're not going to notice it is because your game here is running at 60 frames per second, or at least mine is. And at 60 frames per second, half the distance towards the target is very fast. It's a very fast speed to move at. So what we want to do maybe is choose a smaller distance. So maybe we move 10% of the way towards our target by changing this to 0.1. If you do that and hit F5, you will notice as the ship moves around the screen, the camera plays a little bit of catch-up to it. If you want to, if you're finding that even harder to notice, you could go with even smaller numbers. There we go. The camera is moving from 0, 0 to the player's position initially, and there we go. I'm moving it 1% of the way towards the player's ship, and that actually seems to work decently well. There are a couple ways you can improve the exponential slide that I'm not going to show you today. That would be, for example, finding the distance between the two objects and multiplying it by some ratio, like I'm doing here. So this is like 1% of the way. And then determining if that distance is greater than a terminal velocity. So let's say if I were to do this, or let's go back to my example where I said I'm going to move the position of the camera half the distance towards the target. If I were to take this and store it in a speed variable, then find the length of that speed, and if the length of that speed was larger than, say, some terminal velocity, like let's say this would result in it moving at 50 pixels per update, and I only wanted to allow it to move 10 pixels per update, I could then reduce the speed to move in the same direction but only 10 pixels. So you can actually clamp the speed using the exponential slide as well. Well, I think I covered everything I essentially wanted to cover today. There were a couple more examples I probably would have done in class. I hope that this was easy enough to understand. If not, like I said, there are several links where you can do additional reading. You can always shoot me an email. I hope you guys have a great week, and I hope to see you guys next week. All right, take care.